Good morning, students. Um, Welcome to the AAE 468 Advanced Orbital Mechanics course. Today is the 31st of January 2015, and the number here is 9:47 a.m. I've gone through the slides on A313 Mechanics 1 as I suggested you should do. Orbital Mechanics 1 A313 is a strong prerequisite for this course. So to go and revise it if you haven't done that already. We're starting this class with orbits in 3 dimensions. We, of course, know what orbits are. An orbit is the path of a body around another, particularly of spacecraft or planets around another body, and it's usually a curved path. To look at Google Earth here, we see got the Earth there, and if I to put on, then to see what in real life, to see the Earth go in orbit around the Sun. Search for the Sun. Yeah, that's the Sun there. So we know orbit the Sun. So that means it goes around the Sun in that. And while it's going around the Sun, it's also rotating out its own axis. That is what brings about 9. And right now you are getting that digging, almost getting to the point to start getting that. And over there, not too long ago. So, and space here is just space. That means even the Earth is in space. Space is just the vast expanse where everything is located, everything that is planets, stars, asteroids, meteoroids, everything that is created or that is ever present in the universe, where everything is located. So just on the surface of the Earth. So that said, we go back to our slide. Yeah, the bulk of the material from this slide is from the reference text, Orbital Mechanics for Engineering Students. I know Kwasu Library has got the test edition of this textbook. I've also got my own copy of the latest edition as well, Orbital Mechanics for Engineering Students, edition by Howard Curtis. We will occasionally be making references to the latest edition. So I advise and suggest that you can borrow the hard copy from the library for your use. Then it'll be good. If you can borrow it, please just go there to consult it. We'll move on. I'd say, usually, you know, as I always to my lectures, I prepare slides before lectures, maybe like before the lectures. But right now over here, I don't have the time to prepare the slides with the lectures. So some of these videos will be taken just about when I'm making the slides, so that as I'm making the slides, I'm already lecturing. I might give you an insight to how I make my slides. I hope it won't be boring, but it will be interesting. For this part of the beginning part of the course, since I just took some points of this which I gave you already for A313, and incorporated them into this present slide. And have some already made slides to show you now. But occasionally in between, I might be find the slides or doing adding some other things, updating the slides. So the soft copy of this textbook of mechanics for engineering students, I mean the one that I gave to you, I'll also be making reference to it in this video lecture. With our discussions so far, orbital mechanics AAE313 was confined to the orbital plane. That is, everything we were talking about was just in two dimensions. The orbital plane, the gravitating body, and then the orbiting body were all, their motions were all in the orbital plane, confined to two dimensions. So this presentation will present the means of describing such orbits which we studied in two dimensions, not three-dimensional space, which is of course setting for real maneuvers and orbital maneuvers. It will conclude with a bit of a summary of the two disturbances of Earth orbits to the Earth's non-spherical shape. Will by then refer to as the effect of the oblateness of the Earth. Earth is not a perfect sphere; it's got some bulging at its equator. So such physical shape of the Earth, or such deviation of the physical shape of the Earth from the past sphere, have some effects on the on the body motion that we were studying in A313. So we'll look at what such effects have and how such effects have been utilized to place some satellites. So I think this is where I might want to go to the PDF, because if you want to start typing other thing besides what the textbook did. The textbook has done quite well. I don't know what else I could just snip the page and put there. So I think I'll just go right to the textbook and try to read through. I'll be reading out for most of the time, but I hope you will be reading if either the PDF on your own computer or as it is showing here. You will be reading in WhatsApp. So okay, I might just read it out. If I have some kind of comments, I might just say it out too. So we see that of course the chapter that we are on is chapter 4, and it's in 3 dimensions. An outline of the chapter, geocentric extension, declination frame, state vector and the geocentric area frame, orbital elements and state vector, coordinate transformation, tension between geocentric, equatorial, and peripheral frames, effects of the Earth's oblateness. I hope you still remember what a perifocal frame is. A perifocal frame is just a natural frame of reference of the orbit. It is just coincident with that plane. Such words as as eccentric, I hope you know what it means. It just means it's centered at the Earth. Other things I hope are also familiar to you. Rotation and declination might not be as familiar to you as one they will be at the end of this video lecture. We move on to start reading. I might read the first paragraph so that you get along with the speed with which I'm going to be learning what. So I start introduction. The domain of orbital mechanics up to now has been confined to two dimensions, that is to the plane of the orbits themselves. This explores the means of describing orbits in three-dimensional space, which of course is the setting for real missions and orbital maneuvers. Also to be on the orbits of Earth satellites. The applications are to any two trajectories, including the interplanetary missions to be discussed in Chapter 8. At this juncture, I think I just want to quickly over the internet if I can get a very picture which which satellite in orbit around the Earth. So let's see if we can get some, yeah, some. These are quite interesting. We don't have this much satellites all around the Earth. It looks chaotic. One that is not too. Let's use this one. So this is what we are talking about. Here we have like how many satellites around the Earth? 1, 2, 3, 4, 5, 6, 7, 8, 9. So all in their own particular orbits. No, they might just be 1, 2. I need to count the orbits because the picture shows a satellite on its own orbit twice. So the number of satellites here are just 1, 2. Yes, because there are also 4 orbits. What is interesting here is the fact that we have the Earth there as a sphere, and Earth, of course, is in 3 dimensions. And then our discussion of orbits in A13 was centered on just one of these orbits, just of this orbit there. We weren't considering anything which might be, or the rotation of the orbit, some other region away from the plane that the orbit was describing. But that for us to be able to actually understand or be able to put anything in orbit on the Earth, we need to find a way to describe orbits in 3 dimensions so that we'll be able to know how it's oriented in space or how such orbits will be different from some other orbits Earth. Because yes, we have lots and lots of satellites in orbit around Earth, so you can check on for more interesting in the internet, which will bring discussion into better light to you. But this is quite illustrative. So if we go back to PDF and we can read it. So I'm going to read the first sentence of the next paragraph, and then I'll be reading in words. I hope you will also be following by reading in words. Discussion of the ancient concept of the celestial sphere and the use of right ascension and declination to define the position of stars, planets, and other celestial objects on the sphere. The next sentence. contents out because it seems to be interesting to me. And I want to remind you of something that we might have learned before. So this leads to the establishment of the inertial geocentric equatorial frame of reference and the concept of state vector. You still remember that when we defined an inertial frame of reference, we said it's a frame of reference that doesn't have any translational or rotational acceleration being the keyword. We relative to the fixed stars. And we are looking at kinematic quantities reference to such a frame of reference with their absolute values. So now we say we said from this sentence it says we'll be establishing an inertial geocentric equatorial frame of reference. And it's inertial, it's moving related to the fixed stars. Geocentric is fixed to the center of the Earth. Equatorial, that means its plane is just the plane of the equator of the Earth of reference. And then the concept of state vectors. In 313, we got familiar with state vectors, and we said the state vectors are just the position, velocity, and acceleration vectors. So on 6 components of this vector give the instantaneous position, velocity, and velocity of an object relative to the define the characteristics of the orbit. Yeah, when you want something cross orbits, well, that means much more technically down. But what comes to mind immediately is the fact the satellite, which is in a sun synchronous orbit, or which is called the sun synchronous satellite, must be sync with the motion of the Earth as the motion of the sun. That means you should follow just layman terms. We'll get to what it means as more the technical meaning later on, but just the words, that means the satellite is in synchrony with the sun. Geocentric right ascension and declination frame. So if the plane of the Earth's orbit around the sun as stated in figure 4.1. Just quickly go to the internet to try to get a picture which has been used ecliptic plane lens. This is So what it just means then is that if you have like a very advanced view of the orbital plane of the Earth around the Sun, this is what you would see. So that's the Sun and the foci, and then that's the orbital plane. So in 2 dimensions, we are looking at the orbital plane of the Earth. So what we're saying is the ecliptic, that's the ecliptic plane, the orbital plane of the Earth, that's the ecliptic plane. It's not perfectly coincident with the equatorial plane of the Earth. That is, the equator is inclined to the ecliptic plane by this amount, 23.5 degrees. If the plane and the ecliptic plane were to align and then be parallel, then that means the North Pole, this North Pole would have moved to this direction, and then the equatorial plane there would be on the ecliptic plane. The equatorial plane is different from the ecliptic plane. So the ecliptic plane is just an orbital plane of the Earth's revolution around the Sun, and then the equatorial plane, of course, is that plane which divides the Earth into 2 hemispheres, the northern and then the southern hemisphere. But the Earth revolves on the ecliptic plane. The equatorial plane keeps what I want to say is the angle here keeps closing up and then opening up on the other part. That means the equatorial plane at some point will coincide with the ecliptic plane, and then at some point will also be tilted to this side of the ecliptic plane. And that's what brings out the changes is the most noticeable in the very northern hemisphere or the very southern hemisphere. We go on. So, this is the plane of the Earth's orbit around the Sun, as I just explained with those pictures. This axis of rotation, which passes through the north and south poles, is not perpendicular to the ecliptic, as I just showed. It's tilted away by an angle known as the obliquity of the ecliptic, or eta. So the 23.5 degrees or 23.4 degrees, which I showed you, just quickly go back to it again. Is obliquity of the ecliptic plane. So we go on. Therefore, the Earth's equatorial plane and ecliptic intersect along a line which is known as the vernal equinox line. So the vernal equinox line is the OM. So at that point where the equatorial line, ecliptic plane coincide, then that point is called the vernal equinox line. Let me look for vernal equinox. This one is, I think, this one is, so that's the ecliptic plane, and will celestial equator just parallel to the equatorial plane of the Earth later on. just for now, take from it that the celestial equator is parallel and coincident with the geocentric equatorial plane. So that means the point where the plane coincides with the ecliptic plane is the lunar equinox line. So we draw a line right from the center of the Earth all up through that point with a pressure sphere. That is called the vernal equinox line. So the vernal equinox line points where the ecliptic plane, which is the plane of the Earth's orbit around the Sun, coincides with the equatorial plane. So that's the vernal equinox line. On the equinox is the first day of spring in the northern hemisphere, when the sun crosses the equator from south to north. And it's usually around the 21st of March. Equinox is symbolized by the Greek letter gamma. Because the sun on the spring, when the ecliptic plane and the equatorial plane coincide at noon, when the sun is just crossing the equatorial plane, that position is the vernal equinox line, symbolized by the Greek letter gamma. And that day, the number of hours of daylight and darkness is equal, most noticeably in where the number of hours of daylight and night vary a lot. Around the equator, we don't usually see much variation in the hours of daylight and night, but put it in mind and try to counting or noticing the length of the day now, and then when it's moving towards the 21st of March, or precisely on the 21st of March, try to count the number of hours of day and then the number of hours of night, try to see if they are actually equal. It's fairly around 12 hours of day, 12 hours of darkness around the equator. We will continue on the day when the ecliptic and then the equatorial plane coincide. We have equal number of hours per day and night. That's why the equinox, the equinox occurs this year later. Constellation pieces is, you know what constellation of stars mean. If we also can see the pieces in our night sky over the Nigeria. So if we are able to see a picture, to look out for it in the sky. That's a picture for constellation pieces. Can we make this out? When you look at the night sky, try to be able to see this constellation. Or let's see a better image it might. If you can see the constellation. Okay, that shows why it's oh try to observe the night sky and try to see if you can see this pattern of stars and the constellation pieces. And then know that that is the position of the lunar equinox. Or in the night sky during the fall around of September. So you may not be able to see it now. If for any practical purposes, the lunar equinox line may be considered fixed in space. It actually rotates slowly because the Earth's tilted spin axis precesses world around the normal ecliptic. When you say something precesses, that means it's rotating manner that rotating this pen. You see something like that. Not end of the pen is not away from the original point, but this other end is make out a form of circular path. So what precession means. So what we are seeing from there is that the tilted, the Earth tilted spin axis is was from the normal to the ecliptic at the rate of 1.4 degree. So that is it. This is spin axis. This is and it is tilted to the ecliptic by the obliquity. So it precesses around the normal to the ecliptic. That means it moves westward. It precesses westward. That means it moves like that. It's the center of the Earth, staying on one single position, but this line moving around the normal to the ecliptic. And I see why that is the case. So it's interesting to see that it's almost like forming out an imaginary curve. So that is the case. The rate at which it precesses is 1.4 degree per century. This precession is due primarily to the action of the Sun and the Moon on the non-spherical distribution of mass within the Earth. I hope you're reading along as I'm moving the cursor. So the picture, and I'll try to again a bit. The Earth is around the sun. So if the sun were the right of the Earth, then the Earth would be moving in this manner. There is a gravitational force of attraction from the sun, and that is what keeps the Earth in orbit and other planets in orbit around the sun. So the dominant force of attraction is towards the center of the Earth, and that's the one that has been denoted in Earth. But then, because if you have something spinning gradually, the mass, if it's a bulk of mass and it's spinning, the bulk of mass will be concentrated at the equatorial plane. So that means because the Earth is spinning about its own axis, the effect is to kind of like bulge the equatorial regions of the Earth, so that the equatorial diameter is a bit longer than the polar diameter. And what this means then is that the mass, the region over here is closer to the sun than the region of mass over there is at the instant in time that we are looking at. Then this portion of mass is going to be experiencing much more local level, much stronger gravitational pull from the sun, because of course we know that the gravitational force of attraction is the inverse of the distance apart, the square of the distance apart, so that when the distance apart is small, then the force of attraction is greater. When the distance apart is then the force of attraction is lesser. So that means this portion of the Earth will be experiencing much greater force locally than this portion would be experiencing. And once you have some force imbalance around the center, you know you have some kind of movement. So it's like some kind of torque now be in this, which would want to close up this angle between the equatorial plane and the ecliptic plane. Of course, it's visible enough if this force is pulling this side of the Earth, bring it down here, and it's also pulling it to that side. The effect would want to be to close up, which is also the angle there. So if the Earth were not spinning, if it were spinning, that would be the case. This angle would have been closed up. That means the equatorial plane would have been pulled so that it will coincide with the ecliptic plane. But then the Earth is spinning, and it's spinning because of its spin. There's an angular velocity vector which is directed to the northern, the north pole of the. I know, you know, something is spinning. When you apply some force to it, it's kind of like stabilizes. That's the principle of a gyroscope. So we'll see a video shortly. Because the Earth is spinning, it does allow the ecliptic plane to stop with the equatorial plane. What then happens, this is still the moment generated is still there. What happens is the axis of jet spin now surfaces around the ecliptic. It will be moving around the normal ecliptic. In order to explain this better, I'll try to play this view of a gyroscope. And you should have it already, but if you don't, I might be able to send it to you. Or you could from your juniors, the ones in 300 level now. I think it must have been downloaded from the internet. I'm able to play the whole video, but the part that is
this is a gyroscope. Think of a metal wheel mounted on an axle. The axle will spin freely, secured in a metal frame. The device can behave in the most unexpected ways. Bits of this simple mechanism are obvious, and it doesn't seem to have any special capabilities. Try to stand it on end and it falls over. Try like this and it drops. Apply gravity. And all that changes. A simple method to spin the wheel.
Just pause there. Not to be able to understand what we've been talking about better. Imagine that the Earth is now this portion of the spinning portion of the gyroscope. Imagine there was some kind of sphere here, which is spinning as soon as the rope was drawn. So
first thing I notice about the spinning gyroscope is that it resists attempts to change its position. The force appears when.
So now this portion is spinning. It's going to be resisting if I want to change its position, and that's what we're talking about. Because the Earth is spinning and spinning that way, because it is spinning and spinning, the effect of this force is trying to change its position, trying to create this obliquity, will be resisted by the Earth because of its spinning.
Rotate the gyro. Now when I stand it on the tabletop, it stays vertical. The spinning creating a force that holds the gyroscope upright.
Exactly similar to what I've been trying to explain. You see, because of the force of gravity, if you're not spinning, it will just fall over. That is some force will just, of course, the force of gravity will attract maybe portion to the ground or portion to the ground. But because the gyroscope is now spinning, and then the angular velocity vector is directed into normal to the spinning, the plane of the spinning, the gyroscope resists the action of the force trying to pull it down. But because the force is still acting, the gyroscope is now rather precessing about the angle normal to the plane or where the force is coming from. So
the force disappears and the gyroscope falls.
If the Earth were to stop spinning, now it will just respond to the forces trying to bring it down. Because it is still spinning, it will just be pressing about this axis normal to the ecliptic plane where the force trying to change position reside. So the spin X is just like
incremental force to support the gyroscope like this.
Look,
Levitating.
it's just also because it is still spinning. So even the force of gravity is not enough to down just because it is spinning. So it will rather be precessing.
The spinning gyroscope will balance on a string.
Yeah. So I'll probably try to send you this video, or you can set it up on Google and download it, or you can ask from your juniors to let you have it. So going forward, precessing, it also means that a line on the ecliptic and the equatorial plane coincide would also be precessing about will be precessing about some points. Will be this kind of cone around some other points. Let's say this is towards the sun. Let's say away from the sun. And so the position of the sun on the pole of equinox signifies the vernal equinox line. So that means if we were to bring this down, leave the coincidence of the ecliptic and then the equatorial plane on the fourth ring, then if the sun were here, then it would be the vernal equinox line. So what we are trying to say now is because of the precision of X angular momentum, angular velocity axis around the mouth to the ecliptic, the vernal equinox line will also be a kind of precession about some point. So that means the vernal equinox line is not fixed in the night sky, or it's not fixed. So we then exert a talk on the Earth for the same reason as what we just explained here. And the course of the sun and the moon is a precession of the spin axis, and gamma, that's the vernal equinox line, a period of about 26,000 years. You wonder why one wants to be concerned about something that has a period of 26,000 years, or if to want to plan a mission to Mars, or like a mission beyond the solar system, which will last for many years, or just like the Rosetta mission, which was launched, the Rosetta spacecraft, which was launched about 10 years ago and just reached its target 10 years later last year. That we have to take into account the fact that things out there are always on the move. If you have an error of an error in calculation, you might just miss whatever the target body is. That means the spacecraft you are sending might get there a little too late or a little too early. A little too late or a little too early means it misses its target. So we need to be bothered or concerned about a precision of all these kind of things. The moon also superimposes a small limitation on the precession. This is of liquidity to vary with a maximum amplitude of 0.0025 degree over a period of 18.6 years. You have noticed that the book here quotes the obliquity to be 23.4 degrees. 3.4 degrees. When I checked somewhere on the internet, that was from my memory of geography. I will said the Earth is tilted at some angle 3.5 degrees. What it just means is that the 23.4 degrees is also always changing, and the period of its change is 18.6 years. 4,000 years ago, when the first recorded astronomical observations were made, it was located in the constellation Aries, the ram. The Gamma is a descent of the ancient Babylonian symbol representing the head of the ram. So that explains to us why they're choosing the Greek letter Gamma to represent the equinox. So this celestial sphere, which we're talking about shortly, everything there. So north and south poles of the fixed sphere correspond to those of the Earth rotating within it. So the Earth's equatorial plane out on the celestial sphere defines the celestial equator. Just like I said before, the celestial equatorial plane coincides with the equatorial plane, that is the Earth's equatorial plane. In the celestial sphere, and that's at the middle of the celestial sphere, with the celestial equator coinciding with the equator. So, if you look into the night sky, that's what you're going to be seeing. Like, it's going to feel as if there's this huge sphere in which the Earth is enclosed, and then you can try to now position every other thing with respect to center of the Earth. So that's the celestial sphere, giant sphere or ball covering the whole of the Earth, and everything is now located in that. Of course, it would be difficult to have like what do I call it? The extent of the vastness of such a sphere, it just goes to wherever you want to get to. So it's that very vast sphere around the whole of the Earth. The Earth's equatorial plane outward onto the celestial sphere defines the celestial equator. Equinox, which lies on the celestial equator, is the origin for measurement of longitude. In the diagram of the celestial sphere, the Earth is that in the middle, and the equinox line, that is the line on which the ecliptic plane and then the equatorial plane of the Earth coincide. The one that's shown here. And if we now measure lines of longitude, we measure it positive to the right of the lunar equinox line. So we want the same way as we say The Greenwich meridian line is 0 degrees as London. And then Nigeria is some kind of degrees to the right or to the east of the Greenwich meridian line. That is the line to measure the latitude and longitudes of places around the world, with reference to some point. That is one thing we are going to be doing for applications of special objects relative to the vernal equinox line. So, if you like it, call it longitudinal lines on the celestial sphere, used to determine the right ascension. So when you're talking about the right ascension, you're just talking about the longitudinal distance, right? From in degrees. Sorry, we'll see that usually measured in hours and minutes from vernal equinox line. Let's continue reading. So the verse gamma is on the celestial equator, which in terms is called ascension, right ascension. So now we understand what right ascension means. Ascension can either be by after RA or R. It's measured in degrees east from the vernal equinox. So degrees east of the equinox. This east of the vernal equinox. So on the celestial sphere is called the declination. So lines of latitude on the celestial, and all they are called declination. So declination is capital EEC or that. And it's positive to the north of the equator and negative to the south of the equator. So this shows how the heavenly bodies appear on the night sky. We hear that this celestial equator and the ecliptic plane. So the point they coincide gives us the point of vernal equinox line. So we know that the sun has been put on that vernal equinox line. And we know that this night sky was started on the first day of spring. Or it could be that it wasn't in the night. This sky was on the spring, and that's what it says there. The sun is located at the intersection of the equatorial and ecliptic planes. So this is the first day of spring. Stars from the Earth that their positions relative to each other appear stationary on the celestial sphere, that is the main reason of defining an inertial frame of reference as that which does not have any internal or rotational acceleration relative to the fixed stars, because we know stars are very, very far away. That their positions don't really change that much, so they appear stationary. So for every other thing that is near to us that is moving, it appears to be much logical to use things that appear to be stationary as reference of any measurement of motion. Memories means the coordinates of celestial bodies as a function of time. 4.1 the ephemeris, the coordinates of celestial bodies of Venus and the Moon as a function of time. So if we go to here, we see that for a given date, the ascension of Venus has been put down and the declination has been put down. Then the Moon, and then the declination. And this has been done for a number of days. So this is an ephemeris of Venus and the Moon. And then so on the location of the vernal equinox at a given time. Of course, since ascension and then the declination are measured with reference to the vernal equinox line. If the equinox line is also moving, means these are dependent on whatever vernal equinox that has been used to measure or compute them. For even the positions of the stars relative to the equinox change slowly with time. So everything is in constant motion. Nothing is per se in a very stationary state. At the time when it was that the sun was at fixed position, but of course now we know that it's also moving. The Earth is revolving and the planets are revolving around. Let's even start from the Moon. As long as the Moon is revolving around the Earth, the atmosphere system is revolving around the Sun. The solar system, that is the Sun with all other things revolving around it, also revolving around some other center somewhere, and that center is also revolving around some other center somewhere. So in fact, maybe we should try to look at Google and see. So go to so Google Sky and try to recognize what this is. This is the Milky Way galaxy, the galaxy which our solar system is. So our system must be some might have put position of our system somewhere, but then we galaxy. And before we delve into the Milky Way galaxy, it might be interesting to see what the Milky Way galaxy might look like if we went further away from it. You see, we are going further away from it. It's stuck to a very single speck where other somewhere else too, and then further, go further, and out. This is certainly not the end of the universe, but this is the end of the only started universe. Of course, we know it's still so huge and so it's still so huge that we probably will never know the extent of the vastness of the whole universe. But then, if we to go back in and to the Milky Way galaxy, that's the Milky Way galaxy somewhere of the Milky Way galaxy, or somewhere there or there, we find our own solar system. And if we go further into the solar system, we might be able to find our own planet, Earth. So we can see that everything is so small on that level. And there's still one more thing that might be interesting for you guys to see.
Multiplayer game that plays in your web browser in the ongoing battle between vampires.
Not about that. It's yes, one. Yes, I used it yesterday. So this also the scale of the universe. It tries to relate the scale that we know it to be on human scale, like around here. This is human scale, and go further beyond the human scale. That is going into the very, very microscopic, and then we can go from the human scale, like bigger than the human scale. So before we go to bigger than the human scale, it might be interesting to see what lies below the human scale. So I'm talking so much. I'll just be moving the cursor inwards and outwards until we will have been able to observe most of the skills. And then when we get to what I want you to see, we are going to back to the lecture. So enjoy. Look at an interesting thing here. If one probably analogy of our net to be similar to what happens on atomic level. On atomic level, we know that electrons are constantly moving around the nucleus. So if the nucleus were to be the sun, then this will also be taken to be planets moving around the sun. So how you know there are some things, some kind of life form live on the electrons and doing the nucleus and their own sun, who knows? But this what we have is almost similar to what we have in space, like on the more gigantic level. So we see we are moving outward, 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 outward. I'll probably just play the music back on. We're getting to the very gigantic scales. Look at what we're seeing here. The sun is very, very huge and gigantic. Seems very gigantic to us. I might even think there are, okay, if looking at Google here and with the sun. So find the sun. Yeah, so that one there was very, very huge relative to this other tiny stars. Of course, we know that the sun looks so huge because it's nearer to us. Some of these stars are in fact bigger than the sun, and we see in this. So that there, and that kind of star there, not as big as the sun. That's our Centauri A is about the same size as the sun, almost about the size of the sun. Look Cyrus A and the sun. But when you look at, if you're able to point the position of Cyrus in night sky, you see it as very tiny. But look at the sun there. That's another star. That star. Look at the sun as a speck, but look at this one here. So huge and gigantic. At times, maybe millions of times bigger than the sun. And then look, there are even other stars which are big, or only going to look at the number of zeros bigger than the sun. And then there are even other ones. And then look, everything is So almost if we are coming from this scale and going inwards, it's as if we are going to the atomic level. We arrive at our own solar system and then on our own Earth, and now having human beings living on the Earth. So it's almost as synonymous as to mean that you have some kind of life around the electrons moving around the nucleus of the atom. So we go far and further out. You see the Milky Way galaxy, the scale, the size. You see, there are even some other galaxies which are bigger than the Milky Way galaxy. Look at the amount of things or amount of scales that we've had to come before we even got to the length scale of the Milky Way galaxy. And Milky Way galaxy is even a very tiny speck. A whole of things. Look. So to the variable obvious. That is what we've been able to observe. There might still be some other things as these portions, or even bigger than all these portions that we've not been able to, or we might never be able to chart because of our limited human capabilities. God is indeed wonderful. So let's go to study that even the position of the stars relative to the equinox changes with time. So everything from what we've been looking at, everything is always in constant motion. Everything is in constant motion. So those stars that appear very fixed to us are also moving towards the center of some galaxy, and the whole galaxy is moving towards the center of some other thing. So that's how everything is. But then, if at the varying length scales, the movement of something very big and very far away might not necessarily translate to very big movements when it comes to scale. So, for all practical purposes, it might be not a bit of error to assume that maybe the stars are fixed in the sky, but they're actually moving. So that is just to show the to give us a real feel of the sentence that Ga is only defined for some time or epoch. That is the vernal equinox line is defined for some time or epoch. So, for example, table 4.2 shows the celestial coordinates of the star Regulus. I think Regulus. So, you can get it. The plus star, how big it is. So that's the sun. Yeah, this one. Look at how it is relative to the sun. So that's the Regulus we are talking about here. So it shows the celestial coordinates of the star Regulus at 5 epochs since AD 1700. So people have already started making correct observations of the night sky, and then beginning the orbits and process of heavenly bodies that time ago. So currently the position of the vernal equinox in the year 2000 is used to define the standard grid of the celestial sphere. We know everything is in constant motion, or we take our own engineering calculations, so it's always good to maybe define the position that will be used for a length of time, and then you make corrections for the known changes in such position with time. So, adding this textbook, this version of the textbook, the vernal equinox lies the position in the year 2000 in current use, and I think it's still in current use now. It varies quite from about 13 degrees to about 11 days, so it's actually moving over a space of about 100 years. In 2025, the position will be updated to that of the year 2050. So it's in a way that we are able to calculate of all these kinds of heavenly objects, and that is just from the equation of two-body motion or the n-body motion that length arising from Newton's law of universal gravitation and then Newton's second law. All that really length in orbital mechanics 1A 313. And with such knowledge, you can just try to make calculations into positions heavenly bodies might have in future, and that the position of the vernal equinox will be 25 years into the future, and such position will be used to make calculations of the movement of measurements of the movement of other heavy bodies or slides in the sky. In 2075, the vernal equinox will be updated to that of year 2100, and so at 50 years intervals. Since observations are made relative to the actual orientation of the Earth, these measurements must be transformed into the standardized celestial frame of reference. Point to suggest the adjustment will be small if the current epoch is within 25 years of the standard Christian epoch. So we look at the state vector and the geocentric equatorial frame. And these vectors are the position vector, the velocity vector, the acceleration vector, the position vector. The velocity vector is the differential of the position vector with time. The acceleration vector is the differential of the velocity vector with time. That means the acceleration vector is the size differential of the position vector with time. So, think the assumptions, I'm not going to say them now, but you know the assumptions and think about them. Think them and see if you are very comfortable with thinking about them and then understanding them. This is the familiar two-body equation from orbital mechanics 1, and r dot dot is just the acceleration vector. That is r, that's the position vector. Where here is the magnitude of the position vector, and mu is gravitational parameter. Dominant gravitating body in the two-body system. we see the length of the same vector and especially those of its time derivatives measured in a non-rotating frame attached to the Earth. I think this should be measured in non-rotating frames attached to the Earth. It's supposed to be able to get their absolute values. When if they were to be measured in a body fixed frame of reference, like a fixed frame of reference onto the satellite, then whatever measurements are made will only be relative values. They won't be absolute values. So if you had an inertial frame of reference, a geocentric inertial frame of reference, then we can make such measurements related to that frame of reference. Commonly used non-rotating right-handed Cartesian coordinate system is a geocentric frame showing figure 4.5. So what I learned about this in the first slide of orbital mechanics 1A 313, relative motion with respect to the non-rotating Earth. So all those equations that we that are valid for our discussions now of the movement light. This is something that is common to use. Geocentric equatorial frame. My equinox line defines the x-axis. Z-axis is normal to the equatorial plane. Equator, and the y-axis is at right angles to the x-axis. So we move the x-axis points in the vertical direction, the xy plane, the Earth's equatorial plane, is the x-axis of rotation and points upward, which is clear from our knowledge of in space, DAK, this time in capital letter, because we are looking just to make them different from other kinds of Cartesian coordinate systems, just to be able to show that these are really celestial geocentric equatorial frame used with the celestial sphere. So that of IJK form a right-handed triad. The non-eccentric equatorial frame serves as an inertial frame for the two-body Earth satellite problem, as in equation 4.1. But you have to note that if such a frame of reference is just truly an inertial frame, so the Earth is always accelerating towards a third body, to something of the moon, if we ignored in the two-body formation. You know, when we say two-body problem is just a problem of determining the motion, so it's solely under the influence of mutual gravitation, solely under the influence of mutual gravitation. So we were letting the fact that there are dominant forces of attraction inside the cell. And that would be the n-body problem, which we saw was quite chaotic and periodic. So in order for us to make some kind of very nice engineering calculate, just assume other things are not affecting the body problem of interest that we are seeing. So in other one might not exactly have a truly inertial frame of reference, because if we were to shift our frame of reference to the center of the sun and think it might be fixed, and I just told you like moments ago that even the center of the sun is accelerating towards the center of some other thing. So if we have to shift that inertial frame of reference to the center of that thing that the sun is accelerating towards, that thing is also accelerating towards the center of some other thing. So put the center of the Earth as the center, the origin of some fixed inertial frame of reference, and this will be good enough for the engineering applications in length scale. In the concentric equatorial frame, the sector is given in component form by R equals xi plus y plus zk. That is R. If something is positioned there, the position is R, and it will have components in the z direction, and then components in the x direction, and then components in y direction. That's A, Y, J, Z, K. And it's just the differential of the position vector. So Vx, Vy, Vz. So that's some component of velocity in the direction, and then in the z direction. If the magnitude of the position vector, then of course, using vector notation, we will have the position vector to be or to be equal to the magnitude times the unit vector in direction of the position. So from this figure, we see that the components of UR, the direction times of R, are found in terms of the right ascension alpha and direction delta as follows. So we try to see come about. Yes, if we have a vector, if we have the position vector to be R equal to then U R. The U R is equal to, that is the unit vector, is equal to the vector by the magnitude. So that the vector to be in this x plus y, but that's supposed to be capital Y, plus z k kappa. All to do is just divide the magnitude of the vector, so you can write the vector in terms of its directional cosine as less L for x over R, and then for y over R, and N for R. We just express the unit vector in direction of the position vector in terms of its directional cosine Ln, where N is equal to x over R, N equal to y over R, and N is equal to z over R. And then from this diagram, we can see that the unit of R, unit of R will also be, or the component of R in the Z direction is equal to R delta. That is component R in the the component of the unit vector UR in direction in the Z, the vector, that is the directional sign of the correct direction cosine of the unit vector R in the Z direction is just equal to sign of this declination angle, so sine delta. I'm saying if you want the component of UR is along this axis, so if it's component in the Z direction, you have to find the sine of this angle, sine delta. So we are saying one equals sine delta, and the component of R in the equatorial plane is the component of UR in the equatorial plane is just the cos of delta, so cos delta. So delta. So if we now want the component of line here, UR in this plane is going to be cos delta. So if we want its component in the x direction, we just have to do cos delta sine alpha. That's the right ascension there. So we have to cos the sine alpha. So that sine alpha, and then m is going to cos delta. Let me make it. So this is cos delta. Sorry, this is cos delta cos alpha, and then delta alpha, as can be seen from here. So if the component of UR in this plane is cos delta, then the component of UR in this axis will be cos delta cos R. Then in that direction it will be cos delta sine alpha. This is the direction of the U vector in this direction. One way, that means we can directly write that substitute all this for R y over R and Z over R, or L M N there. UR to be to delta plus delta sine alpha J delta, so plus delta that is the position vector R is R the magnitude times R. So I don't want to write again. So the times R so that if you have the vector, we can find its magnitude and then try to find its direction cosine and then try to determine its declination and then its right ascension from this, because from here implies that delta, which is the declination, is equal to arc sine, right? And and then cos here cos alpha is L over cos delta. We can find the right ascension from there. That is the ascension alpha equals cos L over cos delta. So I suppose on this PDF it doesn't have some of the more explanation that the version which I have with me here. And just note that since there is arc sine n, there is no quadrant ambiguity by definition, since the declination lies between minus 90 degrees and then plus 90 degrees. That means delta, once you have when you do arc sine n, it's going to give you a definite value of delta, and you are going to be able to define actual declination angle. Because you find arc sine n and it gives you positive, you just know you are in the northern celestial hemisphere. If it gives you a negative value, you know that you are in the northern celestial hemisphere. Since cannot also be negative, I would just advise you to go and read the rest of this portion in the later version, because I'm really running out of time. So we just go on from your 4.5, we see that the components of U are the direction cosines of R, ascent of the right ascension alpha, and the definition delta as follows, the way that I've just shown you in my chair. Therefore, given the state vector, that we're given the position vector and then the velocity vector of satellite, we can then compute the right ascension and declination. That means once you know the position vector of satellite, then you can directly compute its right ascension on the celestial hemisphere and then declination on the celestial hemisphere. Our right ascension and declination alone do not furnish R. That means for you, if you just know the right ascension and declination, you can't directly get the position vector. However, if you have the position vector, you directly go from that to get the direction cosine, that ascension and this is what we are saying. Here, because we have the position vector, we walk our way downwards and get the declination and then get the ascension. But if we just know the right ascension and the declination, we must be able to walk away back. Because obviously, if we know the right ascension and declination, we would only be able to compute UR. We still won't know what R is. So we'll be able to get the position vector. R we know is given by Kepler's first law as a squared over mu 1 E cos theta. When theta is the true anomaly, that means for us to define the object or date vector of satellite, know its declination and then its ascension alone will give us enough information to be able to get its position vector. So we still need further information about its eccentricity, anomaly, its specific angular momentum, or some other parameters which we shall be talking about shortly. So we can make a MATLAB routine to code so that once you have you input the position of that light, you can compute for you the dimension and then the ascension of the satellite, and I will that as an assignment for you guys. The book is the new edition which I have, and then you have in the library. I got the algorithm, and then there's you can go and check the textbook, and I think it's even already done it in the appendix, but I would want you to go through it by yourself, because then will be the only time that you'll be able to learn anything. I wanted to even start it here, but I'm running out of time here. Assignment for you. Go to the textbook on page 193 to write or try to compute the algorithm 4.1 in lab, and then send to me. You can consult yourselves on this assignment since this is the first one. But make sure you send them to me individually and the names on your own code. Try to quickly look at one or quickly finish up by looking at this example. So, example 4.1. If the position of the International Space Station is R equals that, so this is related to an inertia, a geometric inertia, a frame of reference, and this is how you see it on the sky. Sorry, in the sky. What is right ascension and declination? So just go to do is find the magnitude of vector. So the magnitude is the from the center of the Earth, and you find the unit vector in that direction. And then once you have found the unit vector, we can see that there is, which will n is just equal to sine delta, and then delta is just equal to arc sine of that. So basically we found the declination. There's no, this is what I was to get about. There's no trans ambiguity since by definition the declination lies between -90 degrees and +90 degrees, which is precisely the range of the principal values of the arc sine function. It so follows that cos delta cannot be negative. Cos 90, the range of 90 and -90 degrees, then cos delta is a positive of the angles between the range of from 90 to -90 degrees is always going to be positive. So 4.5, that is this equation. The cos delta we've already calculated for delta, so you know what cos delta is, and cos alpha will be equal to the equation 4.5, so that cos alpha is equal to, and but alpha might have the quadrant ambiguity because it varies between 0 and 360 degrees. So in order to actually know the one you are talking about, one might need to do to see the sign of this direction sign. We explore more. I'm running out of time. I can't make enough explanation of that. The right ascension is equal to that second quadrant or equal to that third quadrant. On C, that is what I was trying to drive at. We also assign alpha is negative, which because cos delta can be a negative value. So if the sign alpha is negative, and for a negative sign alpha, then cos alpha will give a value in the third quadrant. So that's 198.4 degrees. If we are provided good enough, for example, to show that once we have the position vectors, we work our way and get the declination and then the right ascension of the orbit. So if we are provided with the state vector at some point, R0, V0 at a given instant, we can determine the state vector at any other time in terms of the initial vector by means of the expressions as F R0 plus G V0, V equal to R0 plus G dot V0. Remember, F dot G naught are the Lagrange coefficients. The coefficients. And remember that we use the Lagrange coefficients to determine the position vector of an orbit at a later instance in time, given the initial values of position vectors. Find the total of 6 components of R0, V0, therefore completely determines the size, shape, and rotation of the orbit. So that is in order to describe the orbit, the size, shape, and orientation, we need some initial values, and then we can use the Lagrange coefficients, and we can also get the declination and then the right ascension. You can do example 4.2 on your own, because I'd like to end the lecture now. It's almost 2 hours. Go example on your own. Simple, and then just read this concluding paragraph of the section we just treated, so that it will set the stage for orbitals and the state vector, which will be in the next video lecture. The first example illustrates the fact that the six quantities of orbital elements comprising the state vector R and completely determine the orbit. That's what you should try to understand from the lecture and then from the workings of the examples there. Other elements may be chosen. The classical orbital elements are introduced and related to the state vector in the next. So please do the assignments which I have given you and try to send them to me by email, and also try to send in your feedback, comments, and questions on the lecture and lessons on how to make it, how to give better experience, and I'll make it a better experience. And like I've told you, subsequent slides, I might be adding some more to this slide, or I'll be making subsequent slides at the end that I'm making the video for the lecture. So you use these videos to body well, and then I hope you stay committed to your studies. So have a nice time. Remember to send me feedback, comments, and questions. Thank you.